This video unifies two data attribution papers into one methodological story. Source from 2024 and Magic from 2025. Both ask the same core question: how would model behavior change if we changed training data? Training data attribution matters for interpretability, debugging, unlearning, and data curation. If we can predict the effect of removing or reweighting points without retraining from scratch, we gain a practical causal lens on model behavior. Both papers formalize a model output function that maps training data weights to a measurement on a trained model. Call that function f of w. Attribution is then approximating f under counterfactual changes to w. A shared evaluation metric is LDS, the linear data modeling score. Sample many random removed data subsets, compare predicted outputs against true retrained outputs, and report Spearman correlation. High LDS means counterfactual predictions are rank faithful. Classical influence functions use implicit differentiation at or near an optimum. They are efficient, but can struggle with nonconvergence, optimizer bias, and multi-stage training. These gaps motivate Source and Magic in different ways. Source starts from unrolled differentiation, then compresses it with approximations. Instead of backpropagating through every optimization step, it partitions training into segments and assumes local stationarity of gradient and Hessian statistics. The unrolled derivative sums per step contributions involving Jacobian chains J from each step to the end and per example gradients. Exact computation is expensive in memory and time, especially for large models and long runs. After segmentation, Source approximates intersegment Jacobian products and within segment terms via expected summaries S-bar and R-bar. This yields a practical closed form that captures training stage effects while avoiding full unroll storage. Practically, Source uses EKFAC to approximate Hessian structure and make matrix functions efficient. This supports checkpoints much fewer than full unrolling, for example 6 checkpoints in their experiments. Magic takes a different route. Rather than approximate influence through surrogate curvature only, it computes the exact influence function for iterative smooth learning algorithms using metagradients. Magic still uses first-order Taylor structure around full data weights. The crucial difference is that the influence term, gradient of f with respect to data weights, is computed exactly through training dynamics instead of approximate implicit closure. Magic leverages replay, which backpropagates through the iterative training graph with memory-efficient state loading. The metagradient with respect to data weights is exactly the influence function in this setup. Magic also introduces single model attribution framing. By fixing randomness sources, irreducible variance is removed, making precise prediction of this model's counterfactual behavior possible in principle. Now compare assumptions. Source tolerates nonconvergence and stage training via segmented unrolling approximations. Magic targets near-optimal prediction under smooth iterative algorithms by exact metagradient computation. Computationally, there is a key trade-off. Magic can be very strong for a small number of query points, but scales linearly with query count. Source is generally approximation-based, but often operationally flexible across complex training pipelines. Empirically, Source reports strong improvements in LDS and subset removal counterfactual evaluations across regression, vision, text classification, and language modeling. Benefits are especially visible when implicit diff assumptions are weakest. Magic reports near-perfect LDS at small data drop fractions in several settings including CIFAR10, GPT-2 on Wikitext, and Gemma instruction tuning. As drop fraction grows, first-order approximation quality naturally decays with distance from the linearization point. A unifying interpretation is this: both methods estimate sensitivity of trained behavior to data weights by propagating derivatives through training dynamics. Source compresses this with segmented statistical summaries. Magic computes it exactly in a smooth iterative regime. When should you use which? Use Magic when you need the highest fidelity local counterfactual prediction and can afford per query metagradient cost with smooth training assumptions. Use Source when training is staged or nonconverged, and you need practical scalable attribution with richer pipeline realism. Failure modes also differ. Magic depends on smooth iterative assumptions, and can be expensive for many queries. Source depends on segmentation and stationarity approximations. Poor segmentation can reduce fidelity. A promising frontier is hybrid attribution. Use exact metagradients on a calibration subset to tune segmentation, damping, or curvature approximations for faster large-scale methods. That could combine magic-level faithfulness with source-level coverage. Final takeaway: these two papers move training data attribution from heuristic scoring toward principled counterfactual estimation. Source broadens applicability across realistic pipelines, while magic raises the fidelity ceiling with exact influence computation. Together, they define a stronger methodological foundation for data-centric model analysis.